Welcome. Today is Friday. Thank God. Friday.
Yep. This week
Yeah.
felt so long.
This week has been going before.
I know.
Oh.
Okay? It's Friday, November the 6th. Okay? This is advanced level chemistry at Spain Park. Okay? For the people around the world that will be watching this video. Okay, I have 67 subscribers.
Oh.
Hey, I'm one of them.
Wow.
Hey, I'm one of them. He didn't tell you how to
You're one of them.
Okay? Yeah. So feel free to subscribe to my channel.
Hey, you gotta tell us to like and subscribe.
Yeah. All right. So yesterday we began looking at the spectrum with our groovy glasses on. Okay. So when we put these glasses on again, what do we see?
Red, white, and blue.
Red, cyan.
Can I have a pair of glasses?
Yeah, right there. Just oh, no, those are. Yeah, there we go. So, the whole point is that we're seeing these continuous, bright line spectrum rather than a continuous spectrum. We're not seeing a rainbow. We're seeing 4 individual, well, you're seeing 3, but there's actually 4 in the visible light spectrum. Okay? So, the question is, how can that be going on? What's happening here? Why? How does hydrogen just give these 4 colors? It was a great mystery. Okay? Light was a mystery. I'm going to tell you a little story. Okay? Yes. Okay?
Classic Mr. Hobbs story.
So, back in the 1600s, late 1600s, when Newton, sorry, thank God, it's got Newton, I want to say Galileo, when Newton was alive, okay, light was a mystery because light goes through a vacuum, goes through space, but sound waves don't, okay? But what is light then? How can it go through, how can it go through, if it doesn't have a medium on it? Remember, a vacuum is nothing. So, Newton just came up with his 3 laws of motion, that everything travels in a straight line unless acted upon by some other force. We call that inertia. Okay, F equals ma, and for every action there's an equal opposite reaction force. It's 3 laws of motion. Okay, so Newton proposed, light must be a particle. Light must be some kind of this little tiny particle that's flying through space that travels in a straight line. When it hits a barrier, it bounces off like a mirror. It bounces off just like a ball bounces off the wall. Okay? And then the only other property was refraction. Does anybody know what refraction of a wave means?
Like when it hits something, it slightly bends off.
It bends, okay? That's what your glasses do. That's actually what the lens on your eyeball does, is it bends the light onto your retina. So it all focuses right on the back of your eyeball. Okay? So Newton proposed, he had talked about gravity as well. And so he said, there must be some kind of gravitational attraction between the light and the water to make it speed up, and that change in speed is what causes it to bend. He was pretty widely, renowned for his science knowledge, so everybody kind of accepted that. But then this young whippersnapper named Christian Huygens comes along, not too many years later, and says, no, I think light is a wave. And he could explain how a wave would travel in a straight line. It's called rectilinear propagation. Okay? It's not important, but light would travel in a straight line. Waves bounce off barriers just like a ball bounces off the wall, follows the same thing. But for him, he said that when you put light into water, it's going to slow down, not speed up, and that's what's going to cause it to bend. We say it's more optically dense. Light doesn't travel as fast through it. No way of measuring the speed of light at the time. Nobody could really prove one or the other, but Newton was just a little bit more respected, so we kind of said light's a particle. Well, a couple hundred years go by, and then as they're studying more of the characteristics of light, they find out that there are 2 more characteristics, that light has diffraction patterns, which is what you're seeing with these glasses. Diffraction is when a wave goes through 2 different slits, and it bends and then begin overlapping with one another. And it turns out to be shadows, bright line, shadow, bright line, shadow, bright line, shadow. That's a wave property, diffraction. And interference patterns, that when a crest meets a crest, it gets double high. When a trough meets a trough, it gets double low. If a crest meets a trough, it cancels each other out. It's called interference. Waves interfere with one another. Well, that led to, oh, well, maybe light is a wave. But we still have this whole idea of the medium. What's the medium? And now, I have no idea, but somehow, some way, in the late 1800s, James Clerk Maxwell, a Scottish mathematician, is able to explain that light makes its own medium. That light is called electromagnetic radiation. That somehow, some way, when the electricity goes through here and the light's being produced, it generates an electric field in one plane, a magnetic field in another plane, and then the energy is traveled in the third direction. Okay? How do you explain that in terms of math? I have no idea. It's way over my head. But electromagnetic radiation, so it makes the medium. The only way I can visualize this, I don't know, there's been car commercials, but it was probably before you guys were born, I don't know. But driving out in the desert, or have you guys seen the Indiana Jones, where you got to take the step of faith, where he's got to go out and it's not it's not there, but you step out and then all of a sudden the bridge appears. When a car driving in the desert, the road's forming in front of it. That's how I visualize light. That it's making its own medium coming through. Wow, when they figured out a medium, then the wave theory really took off. Finally, they were able to figure out the speed of light. It was really ingenious how they figured out the speed of light. They had two mountaintops. Appreciate the artistry here. Okay? You had a person on this with a flashlight, with a strong beam of light coming out. Okay? I don't know what they used. They didn't have batteries or flashlights back then, but they made some very bright light. It's 22 miles between the mountain peaks. And over here, you have an octagonal mirror. So when the light hits this right here, it bounces straight back. And this guy can see the light. But if we move this mirror, and it's on a pivot, so it can rotate, if we move it just a little bit, then the light's going to shine up in here, and he won't be able to see it. Right? But once this one gets back to this one, then he can see it again. So they began spinning the wheel. And they found out that, how fast they had to spin the mirror in order to make the beam look continuous. So the amount of time it took for the light to go there and back was the same amount of time it took for this to go from here to here. So 44 miles. Now they got really, really close to what the actual speed of light is. Okay, and they weren't exact, but we use lasers and everything now, a lot more specific information. So they got the speed of light in air. Okay? Pretty smart people figured that one out. How to do it without a computer. Then they found the speed of light in water was actually slower than it was in air. That was the final nail in the particle theory. Huygens now says light is a wave. That must be. We can explain everything about light in terms of its wave nature. Okay? Heinrich Hertz then, at the turn of the century, makes a statement and says, we now know everything there is to know about physics. All we have to do is improve our measuring devices. Little did he know that just a few short years later, he did an experiment called the photoelectric effect. Okay? And the photoelectric effect threw a monkey wrench into everything. So we're going to do a little exercise right now, again on your Chromebook, dealing with the photoelectric effect. What do you think the photoelectric effect deals with?
Light and electricity.
Light and electricity, that's exactly right. The photoelectric effect basically is how a solar powered calculator works. You shine light onto a metal surface, it knocks electrons off and starts the flow of electrons, which we call electricity. But this activity will kind of explain a lot about that. You have to go, I don't think I have the link on Classroom, so you got to probably type it all in. Sorry. Mr. Sluss was supposed to be doing this.
Yes.
You typed it in right the first time, is that what you're excited about? Yeah. That's what I do, I'll mess it up all the time.